The Guelph Permeameter is a constant head test based upon the Mariott bottle principle to evaluate shallow porous media properties of soils and shallow superficial geology deposits. The Mariott bottle principle is a vessel of water which is sealed at the top from the atmosphere and controlled by a valve at the base outlet. A standpipe or an air tube penetrates through the upper cap of the bottle, which is open to the atmosphere through the length of the air tube. This creates atmospheric pressure conditions at the base of the air tube. Atmospheric pressure is also observed at the outflow side of the valve at the base of the apparatus. A vacuum is created in the airspace at the top of the bottle if the water level were to drop in the reservoir column. When the valve is opened, the water level in the Mariott bottle begins to decrease, and the flow emanating from the bottle does so at a constant velocity v, which is equal to the square root of twice the gravitational acceleration times delta h, where delta h is the pressure head difference between the base of the air tube and the outlet valve. As the water level in the vertical column decreases, a negative pressure is induced in the airspace above. The pressure is equilibrated by air entering the water column from the base of the air tube in the form of bubbles. This apparatus is in contrast to a falling head test where the water surface at the top of the column of water is open to the atmosphere and delta H vertically expands from the water surface to the outlet valve. When the valve is open, the water surface in the column begins to decrease and thus delta H decreases. As a result, the velocity of the water that discharges past the valve decreases as the hydraulic head delta H decreases, since the velocity v is still again equal to the square root of twice the gravitational acceleration times delta H. This is illustrated by the change in the flow jet parabola with time. The Guelph Permeameter is an adaptation of the Mariott bottle whereby a modified reservoir has been configured. The reservoir is sealed at the top. The standpipe or air tube penetrates through the closed top of the reservoir, which is open to the atmosphere all along the length of the air tube. The air head space at the top of the reservoir then generates a vacuum if the water level begins to decrease in the reservoir tube. Here, rather than the reservoir being controlled by a valve at the bottom of the apparatus, the device is lowered into a shallow borehole created in a geological medium of interest to be evaluated. The air tube is raised to a desired height which allows water to flow into the borehole until such a condition is reached that the water level in both the borehole and the base of the air tube are in equilibrium at atmospheric pressure. The hydraulic head created between the base of the borehole and the bottom of the air tube is equal to delta H, which remains constant for the experiment. Here, rather than a valve controlling the apparatus rate of flow, the porous media controls the rate of flow away from the borehole. As the water level in the borehole begins to decrease, a partial vacuum is created at the top of the reservoir. The pressure condition in the reservoir is equilibrated by air entering the reservoir from the base of the air tube in the form of bubbles. The field investigation begins by the selection of a desired site and the excavation of a borehole. A relatively coarse auger known as the riverside auger is used to excavate the borehole, typically down to the length of the auger stem, usually between 20 to 25 centimeters below ground surface. It is of note, with adaptations and extensions to the auger apparatus, deeper boreholes can be excavated and tests undertaken. Once the rough borehole has been created, a second and smoother auger is used, known as a sizing or finishing auger. This auger is gently used at the base of the borehole to better fashion the hole into a more consistent circular column, as the dimensions of the borehole will be used in the ensuing calculations. Unfortunately, the sizing auger has a tendency to smear the walls and bottom of the borehole, covering over many of the interstitial spaces and pores, which can adversely affect the measurements. To correct for these deficiencies as best as possible, a well-prepped brush is used to scour away the surface layer of the borehole to expose the interstitial spaces and pores to the surrounding porous media for greater in situ representation of the geological media. The depth of the finished borehole is measured, in this case, 22 centimeters. The Guelph Permeameter is now assembled over the borehole. In this case, since the soil is of a relatively sandy silt composition, there were no concerns about the borehole collapsing. Otherwise, one would assemble the apparatus close to the borehole and then position it over the borehole once the assembly process was completed. The tripod base of the apparatus is assembled first, followed by the support tube, which is what descends into the borehole and contains the air tube. The main reservoir chambers are then assembled with a small middle tube, being the air tube, inserted down the length of the reservoir. The reservoir system is actually comprised of two subcomponent reservoirs. The outer reservoir, which contains a larger volume of water, is commonly used to test more porous soils, while the inner reservoir, being of a smaller volume, is used to test less permeable soils. The support tube of the permeameter is lowered into the borehole with the reservoir filled. At the base of the support tube, there is a water outlet screen, shown here in yellow, which is required to rest at the base of the borehole. The air tube, which is initially resting at the base of the support tube at the bottom of the screened water outlet, is then raised to the desired hydraulic head, such as 5, 10, 15, or 20 centimeters. The height of the water rises in the borehole to the elevation at the base of the air tube, equilibrating the atmospheric pressure conditions between the reservoir and the borehole. The height from the bottom of the finished borehole to the base of the air tube is the resulting hydraulic head delta H used throughout the test. Now, as the water advects from the borehole into the surrounding porous media, a zone of saturation is created and the water level in the borehole begins to decrease, creating a partial vacuum at the top of the fluid cylinder reservoir. The disequilibrium in the pressure is then corrected by air entering the reservoir in the form of bubbles from the base of the air tube, which allows the water to flow from the reservoir into the borehole while maintaining a constant head delta H. Infiltration from the permeameter into the borehole and thus into the porous media continues over the period of the test. At this time, the reservoir is simply being filled with water. It is recommended to fill the lower support tube slowly at first, here demonstrated with a graduated cylinder. Once the water in the support tube has risen to approximately the height of the top of the tripod, the cylinder can be filled in a bit quicker fashion. It is of note that one could also use a siphon or a small pump to fill the main upper reservoirs. If one looks closely at this point in the demonstration, the rise in water surface in the reservoir columns can be observed.
Okay, so the first step we're going to do is raise up the center tube, which controls the height of the water inside the well, and that's usually done at 5 or 10 centimeter intervals. So we'll measure from the top, which is about, start initially at 4 centimeters. So we'll raise that up. To 14 centimeters. So these bubbles that are coming up now, that's just the displacing the water that was inside. And initially when you start, you want both of these levels to be at the same height. The dial has a couple different positions. The 12 o'clock position is for both reservoirs, and then if I turned it down to the 6 o'clock position, that would be just the inner reservoir only. And typically you would do that if the infiltration rate was very slow. But I'm anticipating that it's going to be fairly quick today, so we'll leave it set at 12 o'clock for this test. So it's kind of finicky, and sometimes you have to draw a little bit of water out just to get the test started. Okay, so now it appears to be running on its own. We'll start the stopwatch. And we'll record an initial height of 4.1 centimeters. It's 1 minute. 4.4. So at 2 minutes, we are at 4.8 centimeters. 5.2. Six centimeters.
The experiment continued all the way up to 60 minutes, or until we actually started to observe a repeatable and consistent rate of change of the water level within the reservoirs themselves. You'll notice in early time we made observations at equal 1 minute intervals, where in later times we actually decreased the interval reading to every 2 minutes to simply ease in the data acquisition process. The rate of change is equal to delta H over delta T, which is merely the change in the water level observed in the reservoir between consecutive time observations, and delta T is simply the difference in the time between consecutive time measurements. Here, the salient information was actually included within the data acquisition process, being the location of where the test was conducted, the date of the test, who the investigator was, the depth of hole, which is the finished borehole that was actually augured in the field, the diameter of the borehole itself, which is typically standard if one is actually using the augers that were supplied with the Guelph Permeameter, and then we identified whether this was a combined reservoir test or if it was simply using the inner reservoir test. Again, the combined reservoir is the inner and the outer reservoirs within the Guelph Permeameter, which are combined together for the investigation. This identifies a reservoir constant use of 35.31 centimeters squared for the surface area of the water level. If we were to choose the inner reservoir for a less permeable soil, we would see that the reservoir constant decreases to 2.18 centimeters squared, which is the cross-sectional area of the inner reservoir. Here we actually did an investigation using the combined reservoir system. The last thing that we require for information is then the water level in the well, or simply delta H. In this case, delta H was identified and set to 10 centimeters. You'll also notice that there's actually the opportunities to do a second head test, and this would be a head test conducted after the first one, but we would be doing this at a different hydraulic head or gradient within the well itself, such as at 15 or 20 centimeters in height. We'll actually return back to this to actually show you how that analysis is undertaken in a moment. In the Analysis tab, most of the information is brought forward from our Data Entry tab. The only other thing that we have to identify within this analysis sheet is whether we were conducting a single head test, which was actually undertaken in this case, or a two head test where we would have repeated the experiment with a different hydraulic gradient. Here we'll identify that we were actually conducting a single head test. The next thing that we have to identify is our single head steady rate of fall. We can return back to the Data Entry tab and then simply scan the delta H over delta T values until we actually find at least 3 consecutive values or more maintaining the same value of delta H over delta T, here identified as 0.25 centimeters per minute. The other alternative that we can actually do is plot the information. If we return back to plotting the rate of change, delta H over delta T, versus our time since the beginning of the experiment, we can then plot those analyses, and we see here that close to the 60-minute mark, we are repeating the values of 0.25 centimeters per minute, which is the value that we'll enter into this cell. The next item that we have to identify within the analysis is what is the soil type that we're actually investigating. From Zhang et al. 1998, there were 4 different soil classifications that were identified, being number 1, a compact structureless or clay material, which is often actually used in clay liners or is associated with lacustrine marine sediments. The second type of soil is a fine textured soil and typically unstructured and may also include fine sands. Number 3, which is the most common soil to use, which is what we'll use here, ranges from clays through loams and also includes unstructured media such as fine-grained sands. This is the most common type of soil classification or soil shape with respect to the hydraulic conductivity that is identified. The fourth option is if one is in a coarse gravelly material such as sands or fine gravels. This may also include soils which have macropores and or desiccation cracks. For here, we're going to choose the standard number 3 soil type, which identifies various values for the coefficients for our relationship for our constant that's actually used in the calculation of our soil moisture saturated hydraulic conductivity calculations, where X, beta, and gamma, and alpha star are going to vary based upon whatever the soil structure is that's selected. If we refer over to the coefficients parameter, we can actually then identify how these parameters actually change as a function of the different soil types that are available, where A is the microscopic capillary length factor based upon the soil type, which is a field identified and a laboratory test investigated shape factor for each of the different soil types. We'll also notice in here that the coefficient factor in here has a subscript I. The I simply identifies whether we're in a single head investigation or a 2-head investigation, whereby we would calculate a coefficient for the single head relationship and then we would recalculate coefficients again for the double head test. The other thing that can be modified in here is making a note that the serial number, it relates to the specific Guelph Permeameter used. These values for the cross-sectional area of the combined reservoir and the inner reservoir might vary slightly between the different manufactured Guelph Permeameters. So there is the ability to change those values if needed with respect to the Guelph Permeameter that's used. And returning back to the analysis sheet, we then identify that for the soil that's selected, the various parameters are identified and related to that particular soil type, and then the single head saturated hydraulic conductivity is calculated and is provided in 3 different units. Also, this single head matrix flux potential is also calculated. And if one were to actually acquire data from the field in the field saturated water content and or the ambient soil water content, which would then require drying in an oven, one could then also calculate the single head test absorptivity. Finally, if one were to return and identify a value for a second head test, let's say for example in here we chose a head test of a 15 centimeter head, and then we were to provide all the information for a second test from our times of observations and our water level changes within the reservoirs, we would then be able to return back to our data analysis sheet, simply select our 2 head test, enter the rate for the second head test or steady state rate. Let's say that was equal to a value of 0.35 centimeters per minute. And then values would be then estimated for the saturated hydraulic conductivity and the matrix flux potential for the single head case and for the 2 head case. And correspondingly, and if we were to have again obtained the information for the saturated water content and the ambient soil water content in the field, we would be able to also calculate the absorptivity for the field condition for the 2 head test. This concludes actually the presentation of the Guelph Permeameter. Thanks for coming to the field with us.